Let's take a look at section 26 on harmonic functions. Okay, we won't really have time for many applications, but this kind of foreshadows some of the applications of this complex variable stuff. We'll define a harmonic function. It's a function from R2 to R, so everything's real. It's got two real inputs and a single real output. By the way, you're familiar with this behavior because the real part of an analytic function and the imaginary part of an analytic function fall into that category. We'll touch on applications a little bit deeper in the book. They touch on the applications a fair amount more. So the definition of such a function as being harmonic is as follows. A real valued function h, mapping R2 into R, is harmonic in an open connected set D of the xy plane if it has continuous partial derivatives of the first and second order and it satisfies the partial differential equation, second partial with respect to x plus second partial with respect to y equals 0 throughout that region. The PDE here, the partial differential equation, is called Laplace's equation. So these words ring familiar: continuous partial derivatives, first and second order derivatives we haven't really dealt with in connection with the analytic stuff just yet. Some applications, and really from where this originally arises, is functions satisfying Laplace's equation describe the distribution of heat. They describe electrostatic potential, and both of these at equilibrium. We got our hands full, but in an applied class, you might see this right-hand side being non-zero, maybe as a function of time. So what the Laplace equation describes from our perspective and the applications we'll glance at right now involve distribution of heat, and think of it as like a two-dimensional plate. So we'll take this region D and treat it as a plate. As an example of a harmonic function, consider t of xy equals e to the negative y sine x. We can take partials easily. Second partial with respect to x, we'll differentiate this sine function a couple of times, becomes a cosine and then a negative sign, returning the negative of what we started with. If we'll take the function and calculate a second derivative with respect to y, here's the y part. The negative sign will come down from the exponential twice, leaving us with what we started with, e to the negative y sine x. So if we add that second partial with respect to x to the second partial with respect to y, the little negative sign right there will show that those sum to 0. And so this is actually a harmonic function. Now, this has applications. Let's introduce an application related to heat. If we'll plug in x equals 0, that sine function will be 0, and so the whole function will be 0. If we plug in x equals pi, that sine function will be 0, and the whole function will be 0. So we're getting out values of 0 along certain lines in the Cartesian plane. If we plug in y equals 0, the exponential function will produce a 1, and we're left with a sine function. So along the x-axis, we get this function to have a profile, a cross-section of sine x. If we take a limit as y approaches infinity, the exponential function, y approaches infinity, this will go to 0 in the limit. And so the limit of the t function will be 0 as y approaches infinity. This function t describes the steady state temperature of a thin plane bounded by the region below. All right, so here we are in the xy plane. It's not the complex plane. That's not the setting for this harmonic function stuff. We'll tie it to the complex setting here shortly, though. So here's the x-axis, the y-axis. We said when x is 0, we get out a t-value, t for temperature, a t-value of 0. When x equals pi, the sine function part was 0. We also get out a t-value of 0 along that boundary. When y equals 0, we're looking along this lower line segment and we're getting out a sine function. And we know throughout the region, throughout the domain, which they're taking to be this infinite unbounded rectangle, bounded below, not bounded above, we're getting the Laplace equation satisfied. And also when y gets large, we get far away from here, that t function is going to 0. That was the behavior in terms of the limit for the parameter y. So what we've got is a temperature distribution. The temperature is held at 0 along the vertical sides. It's determined by half a sine wave on the lower boundary, and then we have this limiting behavior. Such a thing is called a boundary at infinity. Of course, there is no boundary at infinity because there is no at infinity, but that's a verbiage that's common, and it indicates some type of limiting behavior. Now, to make a physically meaningful picture from this, think of it as cold here, cold along this vertical boundary, cold at these endpoints of this lower boundary, and hot as it gets. That sine function takes on a value of 1 halfway in between 0 and pi. So we've got cold, hot, cold with a transition according to the sine function. Cold along these boundaries, cold along these boundaries. And if you'll look back at the function, there was that e to the negative y term that's going to dampen that sine wave as y increases, as we move up in the positive y direction. So we'd end up with cold, hot, cold. If we move up a little bit, we'll have cold. In the center, we'll have less hot. And on the side, we'll have cold again. We move up higher still, we're going to have cold, a little bit warm, cold. So you're getting these profiles that are still determined by a sine function, but it's dampened by the exponential function. To tie this in with the complex stuff, if a function f of z equals u of xy plus iv of xy is analytic in a domain, D, then its component functions, u and v, are harmonic in D. So we can use analytic functions to find harmonic functions by taking the real and imaginary parts. So this ties together the complex stuff with this harmonic stuff, which is all in itself, it's all real. If we'll take the function f of z, for example 2.26.2, the function f of z equals f of x plus iy. Take it to be given as e to the negative y sine x minus I e to the negative y cosine x. Then the real parts and the imaginary parts, the u's and the v's, are easy to pick off. Notice this negative sign here carries along with the v part. We've got the real and imaginary parts, the u's and the v's. We can take partial derivatives easily. It's similar to what we had above. The partial of u with respect to x, the sine becomes a cosine. If we take a partial of v with respect to y, the cosine becomes, with respect to y, the e to the negative y spits out a negative sign. We lose this leading negative sign to give us e to the negative y cosine x as well. So the partial of u with respect to x and the partial of v with respect to y are equal. Of course, this comes up because that's the first half of the Cauchy-Riemann equations. If we take the partial of u with respect to y and the partial of v with respect to x, I'll leave it to you to pause this and think through the details. We get partial of u with respect to y equals a negative of partial of v with respect to x. So this function satisfies the Cauchy-Riemann equations. And each of those partial derivatives being nothing more than exponentials in sines or cosines, those partial derivatives exist, they're continuous. This is valid for any x and y. So this function we've defined up here is actually an entire function. So analytic everywhere, applying the theorem that we just observed, then we know that both this u function and this v function, both of these are harmonic throughout all of R2. Remember, functions are harmonic if they're functions of two real inputs and they produce a real output. So that's the setting for a conversation about harmonic, whereas Analytic, we talk real and imaginary parts. We still got, for the real and imaginary parts, a pair of real numbers in and a single real number out. Of course, we paste them together with the I inserted there to produce a function that gives output that's complex value. And let's cut it there and start a second video for the second half.